For my physics misconception video, I'm going around asking friends and family if there's a difference between an object's mass and an object's weight, and if they answer yes, what is the difference? This is a concept normally covered within the first week of grade 11 physics, but most people are unaware of what the right answer really is. Here are some of the answers I got.
Yes.
Okay, what is the difference?
Okay, well, the weight is like how much it weighs, and the mass is like how much matter it takes up. I like to think so, but I don't really know. Yes.
And what's the difference?
Weight like how much like it weighs, and then mass is like how big or solid.
Yes.
And what's the difference?
Mass is essentially the size, and weight, of course, is how much it weighs.
Okay, so I know there is a difference, but
Do you know what it is?
no.
Okay.
Yes.
Okay, and what's the difference?
I think it has something to do with gravity.
I'm gonna say yes, just because I feel like it's a trick question.
And what is the difference between the two?
That one I don't know.
As you can see from my responses, most people knew that there was a difference between an object's mass and an object's weight, but no one really knew what the difference was. So here's an explanation of the difference between an object's mass and an object's weight. When it comes to measuring an object's mass, mass is a measure of how much matter is in an object, and matter is how much stuff or atoms something is made up of. So let's say I have this box. The box is made up of atoms, or matter, and the mass of the box is how much matter the box is made up of. So anything that takes up space has matter and therefore has mass. The mass of an object can never be zero. If the mass of an object is zero, there would be no matter, and therefore no particles, so the object would simply just not exist. Although on Earth, gravity is acting on all objects, it does not affect the mass of an object. Therefore, the mass of the object is always the same, no matter what external force is acting on it. Mass is a scalar quantity, therefore it has a magnitude, such as 50, and a unit of measure, such as kilograms. So in this case, the box has a mass of 50 kilograms. A lot of the things we measure, such as force and velocity, have directions and need a compass rose. But since mass is not a vector quantity, there is no direction. Therefore, the mass of the object is just simply 50 kilograms. If we put our box on an ordinary balance, it would read 50 kilograms. Therefore, the mass of the box is 50 kilograms. The box does not weigh 50 kilograms. When it comes to an object's weight, the weight of the object is the force of gravity acting on the object. In other words, the force of gravity on an object's mass. The force of gravity on an object can be calculated using the common equation Fg equals mg, where Fg is the force of gravity, m is the mass of the object, and g is the acceleration of gravity acting on the object. The acceleration of gravity, or gravitational field strength, can be calculated by the equation little g equals big G m over r squared, where little g is the acceleration of gravity, or gravitation field strength, big G is a universal gravitation constant, m is the mass of the central body, and r is the distance between the centers of the two bodies. Right now, we will be finding the gravitational field strength on Earth using the equation little g equals big G m over r squared. So, we sub in our universal gravitation constant, which is 6.67 times 10 to the negative 11 meters cubed over kilograms times seconds squared, the mass of the Earth, which is 5.97 times 10 to the 24 kilograms, and divide that by the radius of the Earth squared, which is 6,378.1 kilometers squared, and we get the acceleration of gravity on Earth, which is 9.8 meters per second squared. Now, to find the weight of our box, we will go back to the equation Fg equals mg and sub in the mass of our box, which is 50 kilograms, and the acceleration of gravity on Earth, which is 9.8 meters per second squared. And we get 490 newtons. And since it is a vector, we need a direction. And our direction is towards the center of the Earth. Therefore, the weight of our box on Earth is 490 newtons towards the center of the Earth. Therefore, we can make the connection that although an object's mass is always the same, an object's weight can change. This is because when finding the acceleration of gravity, or gravitational field strength, on a different place, such as a different planet, with a different mass and a different radius, we will acquire a different acceleration or gravitational field strength. When we sub this new acceleration of gravity back into our Fg equals mg equation, we will acquire a different weight. This new weight could be either greater than or less than the weight of the object on Earth. For example, I could have someone standing on a scale on the surface of the Earth and his weight reads 120 newtons. Now, if I put him on the Moon, where the acceleration of gravity is about a sixth of the Earth's, the scale will read that his weight is 20 newtons. Now if I send him floating out in outer space, where there's no acceleration of gravity pushing down on him, he will appear to be weightless. In conclusion, there is a difference between an object's mass and an object's weight, and the difference is that the object's mass is a measure of how much matter is in the object, and the object's weight is the force of gravity on the object's mass.